This conference will now be recorded.
Hello everyone. Today we are going to discuss hybridization. Then the next theory, that is valence bond theory. We will see postulates of valence bond theory and limitations of valence bond theory. Though valence bond theory is already started, but there are several features under VBT that we have discussed and some are still left. For example, we have already seen sigma bond, pi bond and orbital overlap in the previous class. Today we will see hybridization and finally the postulates of VBT and the limitations of this theory. But before starting, I would like to mention one correction. So in the last class, this problem I have discussed, and here we need to choose which of the following isoelectronic isostructure. So here basically the correct answer is the first one, NO3 and CO3 2 minus, that I have already chosen. But when I have done the calculation, that is half steric number for this species, half valence electron number of monovalent species plus minus charge. So if we do this calculation for the first two species that I have already shown in the last class, but the mistake that I have done is in place of valence electron I have mentioned the atomic number, so that will result to wrong steric number. Okay, so now what is the actual calculation for NO3 valence electron central atom nitrogen? So valence electron is 5, number of monovalent atoms 0, there is no charge, one charge, so plus 1 because of this negative charge. So it is basically 6 by 2 3. So steric number last day by mistake I have shown it is 4, but actually it is 3. So basically it will be planar triagonal. Okay, and steric number for carbonate 2 negative. Now the central atom is carbon, valence electron for carbon is 4, then 4, number of monovalent atoms 0, and there is 2 negative charge, so plus 2. So this is also giving same steric number, which is 3. So remember, make the please notice the correction. Steric number will be 3 for both, but last day by mistake I have shown it as 4, which is not correct. Okay, so hybridization. Hybridization, this concept that is under VBT. Fine. So there are different features. Some of the features of VBT we have finished, that is orbital overlap, sigma bond, pi bond, and now we are starting the concept hybridization. When it is simple molecule, suppose hydrogen or fluorine, or even if you consider oxygen, these are very simple diatomic molecules, right? So in these cases, you can explain the bonding on the basis of overlap of respective atomic orbitals. So if it is hydrogen and fluorine molecule, we know for hydrogen, sorry, so for hydrogen there is one s orbital and another one s orbital, so this will be the overlap. So in this way you can understand how the orbital overlap is occurring, and there is two unpaired electron which are paired up after bond formation. Okay, so these are very simple to explain. Similarly, if you consider fluorine, fluorine has total 7 valence electron, but that is 2s2 2p5, that is the configuration, total valence electron 7, but only one electron from 2p orbital, like this, total 5, so only one unpaired electron that will interact and together they will form this type of bond. So this is very easily we can explain. We just have to consider the atomic orbital for individual atom, and then we can easily understand how the bonding is occurring. But if we consider polyatomic molecules such as ammonia, CH4, BeCl2, polyatomic, more than 2 atoms are present. So these are not so simple like H2 molecule or F2 molecule. Now they are comparatively complex. So in these cases, just based on the same ground, if you are trying to do the bonding, there is some problem. Okay, and also some of the features may not match with the experimental observation. So what to do in those cases, that we have to see. So as I have mentioned, sometimes there may be experimental problem which indicates that just based on the simple logic that we have applied for H2F2, that we cannot do in complex molecules. So just take the example of methane. It has tetrahedral structure, that is fine, experimental observation. And here the 4 CH bonds that are present, total 4 carbon hydrogen bonds present. They are equivalent, but that is, all these carbon hydrogen bonds are similar type. But this cannot be explained on the basis of overlap of atomic orbitals of H and the atomic orbitals of carbon with different energies. Because if you consider carbon, it has electronic configuration 1s2, 2s2, 2p2. But I am just writing the outermost configuration, which is 2s2, 2p2. That means this 4 carbon hydrogen bond that you will be getting here, carbon will use 4 electrons for formation of 4 CH bonds, right? 4 CH bonds, and carbon will use 1 electron, like this. And hydrogen, it has only 1 electron in 1s, very simple. But see here, electrons types are different. You have 2 s electron and you have 2 p electron. But so electrons, their atomic orbitals are not same, right? But when we are considering the experimental result, all the 4 CH bonds are equivalent. Then how it is matching with the experimental observations? Because experimental observation is saying all these bonds are similar type. But here carbon will be using s or 2s electron for 2 bond formation, and it will be using 2p orbital for other 2 bond formation. So it is not matching with experimental observation. So now we have to consider the concept of hybridization. So in order to explain these observed facts, what we have to do, basically Linus Pauling proposed that the valence atomic orbitals in the molecules, for example in the molecule CH4, they are different from those in the isolated atom. So CH4, here you have only 1 carbon, but carbon is not isolated atom, it is part of CH4. So when it is isolated carbon and when it is present in the molecule CH4, these two case scenario are not same. So valence atomic orbitals, just take carbon 2s, 2p. When it is present in molecule, obviously it is different compared to when it is isolated. So that is the reason now we have to consider, we have to introduce the concept of hybridization. Okay. So in hybridization process, what happens? The atomic orbitals that are having comparable energy. It is not that all the atomic orbitals are having comparable energy. It has to be, that is, their energy must be close to each other. Then only you can combine them and you can hybridize them. Fine. So atomic orbitals having comparable energy, but remember, not equivalent. So it is not equivalent but comparable energy. Combined mathematically, some mathematical calculations are involved. We will not go to that, but it is involved. So when it is combined to produce sets of equivalent orbitals that are properly oriented to form bonds. Okay, so that is actually hybridization. So for carbon, you have 2s orbital, you have 2p orbital. So what will happen? Now these 2s, it will combine with the p orbitals. Fine. So look at this picture. In the left hand side, here we have 2s orbital and 2p orbital. Though you may think that why in 2s there is only one electron, but remember, it is true that the configuration is 2s2 2p2 like this, but that is in ground state. When it is excited state, this electron will be transferred to 2p. So that is why now in 2s there is a single unpaired electron, and in 2p there is 3 unpaired electron. And see here, if you consider this is the energy, 2p is having slightly higher energy compared to 2s, but it is not very highly different from each other from energy point of view. They are close to each other, but still they are not equivalent. So what you will do, you will take one s orbital and you will take 3p orbital and you will hybridize them. As a result, after hybridization, what you will be getting? You will be getting 4 separate sp3 orbital. First sp3, then second sp3, third sp3, 4 sp3. Now all these sp3, they will contain one electron. And see, individually 2s it looks like this spherical, and 2p is like this. But when you are hybridizing them, that is you are mixing them, now the 4 newly generated sp3 orbitals, they will look like this. See how it looks? It is not exactly like 2p. Both the lobes are not same. So initially 4 orbitals are mixed, and finally what you are getting? 4 newly generated sp3 hybrid orbitals. So when you are combining 1s and 3p, that is 3 plus 1 is equal to 4, obviously you will get 4. Number will be remaining same. So these new combinations are called hybrid atomic orbitals. They are no longer pure atomic orbitals. They are now hybrid atomic orbitals. And they possess maximum symmetry, and their orientation in space is such that they can minimize the force of repulsion between the electrons. We know there is different types of interaction, right? BP-BP, LP-BP, LP-LP. So after hybridization, these newly generated orbitals, the significance is that they are now more symmetric in nature, and their orientation in space is, that is, they are beautifully oriented in space so that they can minimize the force of repulsion between electrons, whether BP or LP electrons. Fine. So this is the importance of hybridization, or you can say this is the requirement of hybridization when it is polyatomic molecules, not simple molecules like H2 or F2. Okay. So in this case, what type of hybridization we are getting? We are getting sp3 hybridization. Why sp3? Because you have taken 1s and 3p, so that is why it is sp3. Suppose instead of taking 1s and 3p, if you have taken 1s and 1p, then it will be sp. So different possibilities are there. Okay. So next you will see, first consider this picture sp3 orbital. So this is first sp3, second sp3, third sp3, fourth sp3. So carbon will be utilizing all these 4 sp3. See here carbon is present and it is oriented in such a way. Now the 4 1s orbital of hydrogen, it will be interacting with this, and they will be forming total 4 sigma bonds. So this is carbon and these 4 are hydrogen. So 4 sigma bonds are formed, and that is by the combination of sp3, which is coming from carbon, and pure s orbital, which is coming from hydrogen. Okay, and the angle is 109.5. Similarly, next another possibility we will see for the molecule acetylene. Acetylene is this molecule, H, single bond C, triple bond C, again single bond hydrogen. This is acetylene molecule, organic molecule. Now we have a triple bond between 2 carbon atoms, and in this case both the carbon atoms sp hybridized. So how we are getting this, that we will see. We know it is that is carbon is having configuration 2s2 2p2, but in excited state we can write it like this. Now we will take only one s and one p, and we will mix it. So ultimately what you will be getting? You will be getting 2 sp. So see, this is one sp, this is another sp. Fine. And these 2 electrons, that is rest of the 2 electrons which you have not included in hybridization, you can call them as unhybridized p orbital. They are not part of orbital. And remember one important thing, very very important, this unhybridized p orbital is always involved in pi bond formation. Okay, you will never see any hybrid orbital it is part of pi bond. Always the orbital which is not included in hybridization, that will be taking part in pi bond formation. So here between 2 carbon you can see total 3 bonds. Out of these 3 bonds there is 1 sigma and there is 2 pi bonds. One thing I have mentioned in the last class, whenever you will have any multiple bond, suppose you have CC double bond or you have CC triple bond, one of these bond is sigma, another one is pi. And when it is triple bond, 1 sigma and 2 pi. Okay. So here we have 1 sigma and 2 pi. So each carbon atom, it will be using its 2 sp hybrid orbital. One will be used for sigma bond formation with hydrogen. Another will be used, suppose I am talking about the first carbon. I am giving a star mark here. So if I am considering this carbon, which is having 2 sp, 1 sp will be utilized for bond formation with the hydrogen. Another sp will be utilized for bond formation with the second carbon. Similarly, if you consider the right hand side carbon, it will be using out of 2 sp, 1 sp will be utilized for sigma bond formation with hydrogen and the second sp will be utilized for bond formation with the left hand side carbon. And for this carbon, there is still 2 p orbital that are not part of hybridization, that will be used for this 2 pi bond. Now if you look at the right hand side picture, so here we have these 2 carbon atoms. 1 sp it is using for bond formation with hydrogen, so this is sigma bond. Another sp it is utilizing for this sigma bond. Now come to the right hand side carbon, 1 sp utilize same thing for this sigma, and another sigma is with the left hand side carbon. And the remaining p orbital, that is 2 remaining p orbitals are there. Suppose one p orbital is this green one, it may be y, x, whatever it is. Suppose if you have chosen px as your hybrid orbital, obviously now py and pz, they are not part of hybridization. So py and pz, py is forming this green pi bond and the pz is forming this blue pi bond. Because the molecular axis, that is a sigma bond, the p orbital that you have used for hybridization, that p is basically px. So the remaining p orbitals are py and z, which will be forming pi bond. So py and pz, these two are forming pi bond, and you have chosen x-axis. So this is the x-axis because here you have this molecular axis which is responsible for this sigma bond. That is, px is not directly involved in sigma bond. First it is mixed with s and then we are getting 2 sp which is involved in sigma bond formation. Okay, so this is the orbital diagram for acetylene. Orbital diagram means instead of writing the structure like this, now you have drawn all the orbitals. So that is why I am saying it is orbital diagram. It is not a structure. We have not drawn the bonds, we have drawn the orbitals. Okay, so here the purple orbital is sp, which is sigma bond, and the blue and green, these two colors, they are signifying pi bond. Okay, so here you can also see how the orbitals are mixed. So 2s and one of these p, suppose it is PZ, sorry, PX that you have chosen for mixing, and these two are not part of hybridization. So these two are still left. Okay. So in this way, you can also consider sp2 that I have not shown, but you can consider. Next example that we are going to discuss. In this case, you will see it is not 2s2. Now we have chosen atom phosphorus. So obviously there will be some molecule involving phosphorus, and phosphorus is from third period. So the valence orbitals you have to now consider 3s 3p. So phosphorus, it is from group 15. So valence electron will be 5, and it has valence electron 3s 3p3 like this. Okay. And remember, as it is third period, there is also presence of D. Though it is true that the 3D is vacant, but it is available. In case of second period, there is no such D orbital, right? But here, though it is vacant, but it is available. So why I am saying so? Because as it is available, now there is a probability that you can involve D orbital also in mixing of orbitals. That is, in hybridization process, now you can also take 3D orbital for mixing. So here 3s 2 electrons, 3p 3 electrons, and out of 5 3D we have taken only 1. These 4 are not part of hybridization. Now you have taken 1s, 3p and 1d. See, if you add 1 plus 3 plus 1, how many you are getting? Total 5. That means the newly generated hybrid orbitals total number will be 1, 2, 3, 4, 5. And all these are basically 5 sp3d. So name is sp3d because we have taken 1s, 3p and 1d. Now which molecule we are going to discuss? Obviously, as there is total 5 sp3d, there should be total 5 phosphorus, and with another atom there will be total 5 bonds. So you can take the example of PCl3. So here we have all these hybrid orbitals. So the purple orbitals that you are seeing, these orbitals are basically all these 5 hybrid orbitals. Now as it is total 5 positions, right? 5 hybrid orbitals are used, total 5 positions are there. Remember, when steric number is 5, which structure we get? We get trigonal bipyramidal. So this should be the structure of PCl5. So now in this way you can correlate steric number and hybridization. In the previous class we have seen how to calculate steric number, and accordingly you can draw the geometry. But now you can also combine the concept of hybridization and you can find some correlation between steric number and hybridization. So when it is 5 sp3d, that means 5 positions will be available for bond formation. So here we have this TBP geometry, and all these green orbitals are basically coming from chlorine. So chlorine is basically using, one chlorine is using its 3p orbital. Remember, for chlorine the configuration is 3s2 3p5, and out of 5 electrons, 1 electron of chlorine, it is used up for bond formation with phosphorus, and phosphorus is using all these 5 electrons in this purple colored hybrid orbitals, and the green orbitals are coming from chlorine, which is nothing but 3p. Okay. Now see, this is comparatively a very complex molecule where you can find all the hybridization of all the atoms. So which molecule it is? Can you recognize which molecule it is? See, we have carbon and we have oxygen also. So this is C double bond O. This is basically an organic molecule. Then with this C, there is one carbon in the left hand side, one carbon in the right hand side. Then if you focus on the left hand side carbon, there is 3 bonds with 3 hydrogen. Similar is the case in the right hand side carbon, 3 carbon hydrogen bond. So which molecule it is? Very simple. Ketone molecule, it is acetone. The first member of acetone, the simplest acetone possible. Acetone generalized structure is RCOR, where carbonyl group, both sides there should be alkyl group. So which alkyl group we have? We have 2 methyl group both sides. So if you just compare this molecule that I have drawn just, that is acetone molecule CH3, COCH3 with the orbital diagram in the right hand side. So now I will show how it is possible. So this carbon is basically this one, which is sp2 hybridized. Now when it is sp2 hybridized, okay, let me first say what is the hybridization for all these. Oxygen is also sp2. So these two are sp2. Now this carbon is sp3. This is also sp3. And for hydrogen, there is only one s orbital. So this carbon is sp2. This is also sp2, and the both side, this is sp3, this is also sp3. Now when it is sp3, we know there will be total 4 sp3. So this sp3 hybridized carbon, it is using all its 4 sp3 for bond formation with 3 sp3 used up for bond formation with hydrogen, and the 4th sp3 is used up for this cc bond formation. Similar is the case also for this left hand side part. Now what about this middle carbon, which is sp2? So sp2 means what? 1s, and out of 3p, only 2p orbitals are taken. That means this p orbital is not part of hybridization, and that will be involved in pi bond. So carbon is, this middle carbon is using 3 sp2 orbital for 3 sigma bond formation. The first sp2, it is forming bond with left hand side carbon. Second sp2, suppose it is forming bond with right hand side carbon, and the third sp2 is used up for sigma bond with oxygen. And this pi bond, that is this electron that will be remaining here, that will be used up for bond formation, pi bond formation with oxygen. So one of this bond is pi, another one is sigma. So 3 sigma for this middle carbon, 3 sigma by 3 sp2, and 1 pi orbital, which is from this unhybridized p orbital, that is which is not part of hybridization. And if you focus on oxygen, now let me write the hybridization for oxygen. So oxygen total valence electron 6. I will write directly the excited state. Total 6 electron. Fine. So it will be now you can also write it like this. If you are not comfortable with this, you can also write it like this. So 2s2, 2p, 4. Fine. Now there will be sp2 hybridization. That means one p orbital will not take part in hybridization, and that will be involved in pi bond. So we are getting total 3 sp2. So the oxygen, there is only one sigma bond with carbon. So one sp2 will be used up for bond formation with carbon, sigma bond. These two sp2, they will be containing the lone pair, because when you are doing the hybridization, total 5 electrons are there. So one electron will be in one sp2, then this is a lone pair, then another lone pair. So these two lone pair will be residing in 2 sp2 remaining. The first sp2 is used up for sigma bond formation with carbon, and the p orbital, which is not part of hybridization, that will be used up for pi bond formation with carbon. So in this way you can explain the hybridization of all the carbon atoms, oxygen atoms in the molecule acetone. Now, as I have said, that you can find some correlation between steric number and geometry. Until now, we have seen when you know steric number, how to what will be the corresponding geometry, that we have seen in VSEPR. But in this case, you can also see I have mentioned the hybridization. In the bracket, steric numbers are also mentioned. So when steric number is 2, it will be SP. When it is 3, it is SP2. Now under that is when steric number is 4, two different possibilities are there. That is two different type of hybridization. One hybridization with steric number 4 that you have already seen in case of methane. Okay, but there is another possibility if d orbital is available, dsp2, that means 1s, 2p and 1d. Now this type of hybridization normally you will not see for p block elements. It is mainly observed for d block elements, and in this case it is square planar. That means if it is suppose type AB4, it will have geometry like this, square planar. So this is a square which is in a plane, so that is a square planar. But remember, this type of geometry is mainly observed for transition elements. Okay. Then for steric number 5, this is the hybridization, and you can, it is not that you just have to memorize it, you can easily understand it also, because when it is 5, it is basically 1s, 3p, 1d, that means total is 5. Then when it is 6, sp3d2, 1s, 3p, 2d, just add all this, you will get 6. Now under 6, there is another possibility also, which is d2sp3, but all these details, that is beyond D2 sp3 D2, these two are mainly you will get not in transition elements, though 7 you can get, but under 6 these two possibilities, that is when it is sp3 D2 or when it is D2 sp3, all this discussion is basically related to D block elements, not in this chapter you will find it. Similarly, when it is 4, out of these two, which one you should consider? DSP2 you will not see in case of P block elements, and in this unit it is mainly P block elements where you will apply the VBT. VBT you can also find for D block elements, but there you will see different types of examples. So all these examples that you will find in this unit, it is mainly from P block elements. Fine. So postulates of valence bond theory. So under valence bond theory, which is we have started after VSEPR theory. Remember, first we have seen Lewis theory, then VSEPR. Now this is the third one. So here under this we have seen orbital overlap. Then we have seen sigma bond, pi bond, and finally hybridization in today's class that you have seen. So if we summarize all these things, whatever we have learned under valence bond theory, if you summarize this, now you can consider these postulates. So in this case, half-filled orbitals of two atoms overlap. Take the example of hydrogen, very simple. One electron present in one s orbital, for other one same thing, and there is a formation of covalent bond between them. The resultant overlapping, and it is not that you have to consider H2, you can also consider the examples that right now we have discussed. For example, CH4, or you can consider PCl3. So in PCl3, what you have seen? You have total 5 sp3d, but each sp3d there is a single electron. That means it is half-filled hybrid orbital of phosphorus, which is overlapping with p orbital of chlorine. That means from phosphorus there is one electron, from chlorine there is another electron. Phosphorus is using its sp3d orbital, chlorine is using its p orbital, and now there is bond formation between them. So you can consider PCl3 or CH4 or H2, but half-filled orbitals of two different atoms overlapping, and there is sharing of electron, and as a result covalent bond is formed. Now the resultant overlapping orbital is occupied by two electrons with opposite spin. So once the bond between these two atoms are formed, once the bond is formed like this, that is PCl bond, you can consider from the molecule PCl5. Once the bond is formed, the electrons will be like this. with opposite spin. Now, how to know the strength of covalent bond? That actually depends on the extent of overlap. So when it is highly, that is, they are overlapping with each other, the extent is very high, then obviously the strength of the bond is high. So greater is the overlap, larger is the energy release, and stronger will be the bond formed. Okay, and also it will be shorter, its length will be short. Each atomic orbital has a specific direction except s orbital, which is spherical. So s orbital is spherical, but remember in last class we have seen when it is p orbital, d orbital, different, that is lobes are having different direction. For example, when it is p orbital, this is the lobe. For s it is simple, it is spherical. Then for d, in 4 direction lobes are present. So orbitals are having some specific direction except s, and hence orbital overlap takes place in that direction and it will maximize overlap. So if you are taking to p orbital, you are forming some sigma bond. This is the zone where maximum overlap is taking place. Okay, and that it is because of this type of dumbbell shape. Depends on the specific direction of the lobe or the shape of the lobe. The presence of many unpaired electrons in the valence shell of an atom enables it to form multiple bonds with other atoms. So just take the example of PCl5. So you have total 5 phosphorus chlorine bond, or if you are considering any double bond or triple bond, that is, just take the example of acetylene, where we have seen multiple bond between 2 carbon atoms. So in this case, carbon is having total 4 unpaired electron, and out of this 4 unpaired electron, 2 are involved in sp hybridization. These 2 are pure p orbital. But whatever it is, that is, these 4 unpaired electron, whether they are in hybrid orbital or pure p orbital, these 2 are actually forming pi bond, and these 2 sp, they are forming sigma bond. Okay, so when there is many unpaired electron, so in this case you have 4 unpaired electron in the valence shell, so it will be enabling this atom to form multiple bonds with other atom. The paired electrons present in the valence shell do not participate in the formation of chemical bonds as per the valence bond theory. So what it means? The paired electron present in the valence shell. Suppose there are some electrons present as pair of electrons. Just take the example of acetone molecule in the previous slide, where you have seen oxygen atom, which is sp2 hybridized. Remember this structure. So oxygen is sp2 hybridized, that is true, that is fine. But in this case, the paired electron which is present in sp2 orbital, they are not taking part in bond formation because they are paired electron. So when it is paired electron, obviously they will not be able to form some bond, because for bond formation between 2 atoms, the requirement is 1 unpaired electron from A, 1 unpaired electron from B, then only bond formation is possible. But if in A, in this case you can consider oxygen. So in case of oxygen, there is some paired electron also present in valence shell. So this paired electron, they cannot take part in chemical bond formation. If it is taking part in bond formation, that means the pair must be broken, then only bond formation is possible. So the electrons that are not part of for oxygen, you can see these 2 electrons are not part of bond formation. They are basically pair of electron and they are lone pair, so they do not participate in the formation of chemical bonds as per this theory. Now, just like any other theory, here also you can find some limitations. The theory only explains the formation of covalent bond in which shared pair of electrons comes from 2 bonding atoms. That is AB. This is the electron pair. One is coming from A, another one is coming from B. But remember, there is another type of bond formation also possible, that is, it is already mentioned in this unit, where both the electrons are coming from same atom. And once it has already contributed from B, then they are behaving as covalent bond. So this is covalent bond. But the second one is known as coordinate bond, or sometimes it is also called covalent coordinate bond. But this theory can only explain covalent bond. It cannot explain coordinate bond, where both the electrons contributed by one of the bonded atoms. This is limitation. In this theory, you will be seeing that we are not talking about any energy of the electrons, which an electron is having higher energy, which electron is having lower energy. All these things we have not discussed. So no insight is offered regarding energy. Then it doesn't give quantitative interpretation of the thermodynamic or kinetic stabilities of the coordination compounds. See, this statement, it is mentioned kinetic or thermodynamic stability for coordination compounds. Now consider the first statement. In the first statement, it is already mentioned that it cannot explain coordinate bond. So if it cannot explain coordinate bond, then how it can explain the bonding or stability for coordination compounds? Because coordination compounds means coordinate bond will be present. That is why the name coordination compounds. Okay. And this type of compounds mainly you will find in D block elements. So this limitation, though it is not directly related to this unit, but remember, for coordination compounds, or another way also you can say that for D block elements, the compounds that we get, that is the metal complex or coordination compounds, they are thermodynamic or kinetic stability we cannot interpret. Now thermodynamic and kinetic stability means, first consider thermodynamic stability. So if I am saying a complex is thermodynamically stable, that means the metal, remember for coordination compounds, there is bond between metal and ligand. So suppose there is one metal, suppose it is copper, and there are 4 ligands. It may be 4 chlorine atoms. So this together it is forming Ml4. Now in this formation, how, that is, once that equilibrium is reached, what will be the yield of this compound? That is how, what is the percentage of this Ml4 you will be getting? That is actually the thermodynamic stability. If it is very thermodynamically stable, that is thermodynamic stability is very high, yield will also be high. So this is thermodynamic stability. Once equilibrium is reached, what will be the yield of the product? But if you are talking about kinetic stability, that means now it has nothing to do with equilibriums. So don't consider this equilibrium sign. So kinetic stability means whether this how fast this Ml4 will be formed, okay, or whether there is any chance that it will revert back. So that is kinetics, that is how fast it will be formed or how fast it will be broken. It has nothing to do with yield, how much you will get on that, okay. But whatever it is, this type of stability, whether it is thermodynamic or kinetic, applicable for coordination compounds, this we cannot interpret. That is whether it will be thermally stable or not, kinetically stable or not, all these things you cannot interpret from VBT. Then no explanation for the color exhibited by coordination compounds. Basically all these points that you are seeing here all are related to coordination compounds, and for coordination compounds this theory not applicable at all. So for coordination compounds there are some specific colors we can observe, but why some compounds are showing color, why some of them are not showing color, this you cannot explain. Then no detailed information about the magnetic properties of the complexes. So sometimes it may happen the complex, suppose Ml4 or M prime L4, and different types of complex. It may be copper, nickel, whatever. All these are D block elements. Magnetic property, that means whether they are paramagnetic. Paramagnetic means unpaired electron will be present, or whether they are diamagnetic. This you cannot interpret correctly, okay. So this is actually for complex compounds or coordination compounds, but one example you can also consider from the molecules that we have discussed, which is oxygen. Okay, so this theory fails to explain why O2 is paramagnetic, because O2 is experimentally found to be paramagnetic. Okay, and according to this theory, it is observed that O2 is diamagnetic. That means the result that we are getting for this oxygen molecule, by applying this theory, we are not getting the correct result. Correct result is that it should be paramagnetic. So there must be presence of some unpaired electron. But we are not getting any paramagnetic character. From this theory, we are finding that it is diamagnetic. So that is the problem. Now one problem we'll discuss, which is related to hybridization. So it is saying that the hybridization of atomic orbitals of nitrogen atom, because the three species that are given here, NO2 plus, NO2 minus, NH4 plus, all these three ions, cation, then anion, then again cation, in all these three species, nitrogen is the central atom, isn't it? So we have to find hybridization of the atomic orbitals that nitrogen is using in these three species. Okay, so different options, that is combination of sp2, sp, sp3, all these are mentioned. So the first one should be NO2 plus, because respectively is written. Next one is NO2 minus, last one for ammonium ion, NH4 plus. So in this case, remember, we have used this formula several times, half V plus M plus minus C. And once you know the steric number, you can also predict what should be the corresponding hybridization. So first, if you consider NO2 plus, here steric number should be half. For nitrogen, 5 valence electron. For oxygen, we will not consider anything. And there is positive charge, so it is 5 minus 1. So what you are getting, 4 by 2, that means 2. And 2 means it should be sp. Okay. Now luckily, in option B, the first one is mentioned as sp. All the options it is sp2, sp2. So you can choose this. But we will also see why the other species, what should be the hybridization. 5 plus 0, negative charge, that means plus 1. Now it is 6 by 2. So it is sp2. Okay. For ammonium ion, again 5. Now for hydrogen you have to write. Positive charge, you have to subtract. So 9 minus 1, 8. 8 by 2, 4. So correct option should be the second option, right? So you have to utilize this table, that is hybridization, steric number, geometry. The molecule which has pyramidal shape. Now it is not directly asking you hybridization. So you can simply apply the formula half V plus M plus minus C. And once you know what is the steric number, then also you can find what should be its shape. Or another way also you can find the shape. That is, I'm just simply applying VSEPR. In VSEPR, I have shown two methods. One is you can apply this formula. Another method is, first you have to choose the central atom. Once you have chosen the central atom, next step you have to find total number of valence electron. So just take the example of PCl3. Valence electron should be 5 for the central atom. Okay. Now out of these 5 valence electron, there will be actually hybridization. But without hybridization also, how to consider it? Here I have written the electronic configuration, but even if you do not write it, it's fine. Okay, I'm erasing it. So 5 valence electron. Out of this 5 valence electron, 3 will be used up for bond formation with 3 chlorine, 3 PCl bond. So 3 used up for as bond pair. Remaining electron only 2, which will be 1 lone pair. That means total number of positions 3 plus 1, it is 4. Okay. Next, if you are applying the steric number, that formula, then it should be half 5, then monovalent atoms 3, 8 by 2, then also you are getting 4. So whether you apply any of this method, you are getting steric number 4. And when it is steric number 4, that means total 4 positions will be there. Okay. So 4 positions will be there means what? It is basically tetrahedral. In short, I am writing TD. So it will be 3 positions of tetrahedral, there will be chlorine. Remaining position, as there is 1 lone pair, it will be like this. So geometry is tetrahedral, that is fine. But if you are omitting the lone pair, the remaining shape is basically pyramidal. So this should be the correct option. But if you want to apply hybridization, if you are comfortable in that way, that also you can do. Okay. So steric number, as it is 4, it is tetrahedral, that means it is sp3 hybridized. Apply the table, this table, right hand side. So it is sp3. Now sp3 means what? Again, it means tetrahedral, and tetrahedral means you are reaching the same conclusion. So this should be the correct option. But why not the other 3? In case of SO3, what happens? You can consider any of this method. I am showing the formula. Sulfur is having total 6 valence electrons. So half 6, number of monovalent atoms 0, there is no charge. So it is 6 by 2, that is 3. So it should be sp2 hybridization. That means the structure should be total 3 positions will be there. 3 steric number means total 3 positions. It is planar triagonal, PT. In short, I am writing PT. Okay. It is a particular plane. And if you want to apply, that is 6 valence electron, out of these 6 valent electrons, 3 will be used up for 3 sigma bond. Though there are 3 pi bond, but pi bond will not focus. 3 sigma bond, 3 electrons will be used up. Okay. And don't think that rest of the 3 that will be treated as lone pair, because rest of the 3 will be involved in pi bond. See, when there is multiple bond, then also you can understand it in this way. Or if you directly using the formula, that is also fine. Okay. So 6 valence electron, 3 electron used up for 3 bond pair as sigma, and rest of the 3 used up for 3 bond pair but in pi. Fine. What about CO3 2 minus? For CO3 2 minus, carbon is the central atom, that means half. For carbon, valence electron 4, monovalent atoms not present, 2 negative charge plus 2. So it is 6 by 2, that means 3. So this is also sp2. So this type of shape, planar triagonal. And for NO3 also you will see half, 5, 0, 1 negative charge, 6 by 2, 3. So this should also be planar triagonal. Okay. NO3 minus. Total 2 negative charge, but these 2 will be cancelled. Overall negative charge is only 1. So these 3 are planar triagonal. Only PCl3 is tetrahedral, but as there is 1 lone pair present, so without the lone pair, the remaining shape is pyramidal. Okay. If I draw it in a better way, it will be like this. This is the remaining shape, which is pyramidal. So this should be the correct option. Fine. Now this problem, we probably will not be able to finish it, but I will just start. Even if we can't finish, we will complete it in the next class. Which one of the following compounds has sp2 hybridization? So it is directly asking in which case sp2 hybridization is present. Fine. So this formula we have used several times. Now if you use it for CO2, the steric number will be half. Carbon is central atom, that means 4. Monovalent atom 0, there is no charge, so it is 2. That means it is sp. So CO2, you know, it is linear like this. 2 positions. 2 steric number means 2 positions. And sp is the hybridization. What about SO2? Valence electron for sulfur 6, 0. 6 by 2, 3. So it is sp2. Because according to the table that I have mentioned 2 slides before, there you have already seen when steric number is 3. Basically, see here 1s and 1p, that means 1 plus 1, 2. 1s, 2p, so 1 plus 2, 3. Okay, so sp2 hybridization, and 3 means it is basically planar trigonal, and it will be, so there is a third position also, there will be lone pair present. If you consider from the point of view of valence electron, total 6 valence electron, out of these 6 valent electrons, 2 electron used up for 2 sigma bond, next 2 electrons used up for this pi, because whenever you have double bond there is 1 sigma 1 pi. Okay, and the remaining 2 electrons that will be treated as lone pair. But important point is here, how many positions you have? You have total 3 positions, 1, 2, 3. So 3 position means 3 steric number. So it is sp2 hybridization. But suppose in this case, if it is asking to find out the shape, the remaining shape is like this without the lone pair. Just focus on this part, and it is bent. So though it is not required from question point of view, but I am just giving you extra information that for SO2 molecule, its geometry is planar trigonal, sp2. But without lone pair, as there is a lone pair present, without lone pair, the remaining shape will be bent like this. Okay. And what about these two? Now for these two, I want to discuss it in detail. Though in this question, we have already reached the correct answer, which is sulfur dioxide. So that is fine. Now we don't have to consider N2O and CO. We have already reached our answer. But for further, that is, if you are really want to know what about N2 and CO, because you can also get another question where N2O, CO, all these molecules will be present. So these two molecules, we will see in the next class. Directly you cannot apply this formula because there is some problem. There is triple bond present. So when triple bond present, what we can do, how to reach the correct answer, how to understand what should be the hybridization, all these things we will discuss in the next. So in this case, it is SO2, correct answer. But why N2 and CO, they are not sp2, that we have to see in the next class. Thank you for listening. We are at the end of the session.